So in this video we're going to talk about context switching and with paying particular attention to process switching, and we're also going to introduce a very quick idea of modeling process state. So you should remember the idea of the instruction cycle, so the fetch execute cycle. You should have a vague idea of the fact that we can stop a process by interrupting it and then resume it later. You should have a notion of the memory hierarchy and this idea of caching, I/O techniques, and multiprocessor and multi-core architecture. And you should also have an idea of what the difference is between the term process and thread. So in this video, we're going to talk about context switching, specifically process switching, which occurs in the bottom two quadrants of our little diagram here that we discussed in the last video. So we're talking about the scenario where an operating system may be able to handle having multiple processes running at once, and so it needs to switch in and out between them, and we're going to go through what that means. But a lot of what we're going to discuss also applies to thread switching, which is another form of context switching, which occurs in these two scenarios. But we're not going to talk about them directly, and that'll get discussed more in lecture. Alright, so let's talk about context switching, and we're going to talk about it in the most basic sense that we can, and we're going to talk about it with an example. So let's imagine that we have three processes that the system needs to run. We have process A, whose instructions are stored in this area of memory, so starting at address 5000 and then onwards, obviously somewhere short of 8000. Then we'll have process B, which I'm going to use purple to refer to, and it starts at address 8000. And finally we have process C, lucky orange, starting at address 12,000 in our main memory. We will also have another piece of code which is called the dispatcher. Now the dispatcher, let me pick a good colour, light blue, in this case is residing at an early memory address 100, and it's the set of instructions that we need to run in order to send a process off to run. So when we actually, if we've stopped and we're about to run a process, then we actually do need to execute instructions in order to move the required memory around, load the program counter, etc., in order to start the process off with dispatching. And we call this piece of code the dispatcher. So if the process were to execute, then we can imagine the trace, so the series of instructions being run for each of the processes over here on the left. So we'll say that process A only has 12 instructions from 5000 to 5011. We'll say that process B has a whopping 4 instructions, and process C sitting over here has the same number of instructions. Maybe it continues on, that's not really important. But we can see the trace of these processes, and if it was possible to run them all exactly in parallel, then we could imagine a trace like this of all of the processes running at the same time. So you bright young computer scientists and software engineers can obviously imagine a number of scenarios in which you would need to run several processes concurrently as far as the user is concerned, but where you don't actually have the hardware capable of running multiple processes in parallel, or don't have the hardware capable to run as many processes in parallel as you actually want to. Now, the way we can actually achieve that is through interleaving and interrupting processes. So remember, we talked before about the idea that we can have a process run for a period of steps, and then we should be able to stop it, send its data off, send all of the relevant information about that process to somewhere in memory, and then later reload that process and run it again. And that's what we'll be talking about in this particular example. So for the set of processes A, B, and C that we talked about before, remember we coloured them in this way, I believe. Now we can talk about what that would actually look like in the real trace of processes run by the operating system. So imagine that we've started with process A, and it runs for a series of instructions, but it doesn't quite complete. So it runs up to and finishes instruction 5005. and then for some reason, in this case we have timeout written, but for whatever reason, the operating system has decided that it wants to stop that process there, and it wants to start running process B. So at this point, remember as well that we have this dispatcher process. And in this case, it's going to be a series of 6 instructions that we need to run in order to be able to shuffle off process A and save it somewhere, and then load in the context required for running process B. So those instructions will then execute. And at the end of that, the system is ready to start running process B. So process B runs, and it runs up to and including instruction 8003, and in this case, at this point in time, it sends off an IO request. So it asks for some information or requests to send some information somewhere outside. So this causes the dispatcher to now run again. So the same set of instructions from the dispatcher runs, and we are now ready for, we now have the context ready for instruction C to, process C to run a series of instructions, and in this case it runs the same series of 5 instructions, and in this case again we have a timeout. So obviously we have a system here that is happy to run 6 instructions in a row, but at that point it's going to shuffle off and load the next process. So the dispatcher process is run again, and the next process that's capable of running is process A again. So it starts from the point at which it was interrupted before. So it runs a series of instructions, in this case down to its final trace, but we can imagine that there is another set of instructions further on for process A. And again we have a timeout, the dispatcher series of instructions runs, and then we run the final set of instructions for process C down, and then the process continues on. We can imagine other processes entering the system. Now, some important things that we can see here is that it is possible for us to run multiple processes in concurrently, if not actually in parallel, by running a process for a period of time and then stopping that process and then starting another process that we need to run at the same time, and having a program called a dispatcher which handles all of that swapping information. Now, one of the things that you should notice from this is that there is a significant trade-off. All of these areas shaded in blue are sets of processor time that are being spent not actually executing the processes that we cared about. They're being spent executing the dispatcher. So in order to do this, we do have to pay a cost in loading out the context of the previous process and loading in the context of the next process. And this is called context switch, which is a term we'll discuss more in the lectures. But there is a cost associated with having processes interleaved. And we can see that if we are interrupting too often, we will actually spend most of the CPU time running the dispatcher, in this particular example, then, rather than running useful processes. And we can see that in terms of the overall time taken for the process to run, far more instructions have been executed to execute all of these instructions than would have been needed to just execute the processes if we had run just simply all of process A, all of process B, and all of process C. But we can obviously see that, we can obviously imagine how that would be a terrible scenario to have in reality, to simply be trying to run one process until its conclusion, if that process, for instance, never ends. So there are trade-offs that we need to consider when we're talking about interleaving and threading. It's not a magic bullet. So this might be a good point to have pause and have a breather, but what we're going to start talking about now is process state. So obviously when we were running that series of interleaved processes, one process was running at a time, but the other two processes were sitting off doing something other than running. So we know that we have, in say a single uniprocessor environment, we won't have all of the processes actually running at the same time, even though we are really running them all concurrently as far as we're concerned. So in this situation, the simplest possibility is to have two states to the process. The process can be running, in which case its registers may be modified by the CPU, the process is actually doing something. And the other state is some sort of not running state, so maybe an idle state. It's frozen, stored somewhere for later, the actual program code is not being executed. So in this case, we have two states that the process is switching between. A graphical model for this simple two-state model is shown here. So we have our running and our not running state, and then we can imagine this situation as a finite state machine, where if the process enters the system, we start out in the not running state, because obviously there might be a process already running. When the dispatcher runs and sends that process off, then we can transition the process into the running state. Then if for some reason it's paused, or there is an I/O request, or some reason why the process is stopped in order for another process to run, we transition back into the not running state. And then when we finally finish with the process, that will have occurred at some point that we were running it, we'll now move off and this process won't be concerned anymore. Now, this is the simple two-state model, and we're actually going to introduce more detailed multi-state models that are more reflective of what happens in actual real-life operating systems, because it's not as simple as this. But the idea that a process can be in multiple states as far as its execution is concerned is something that you should keep in mind from this video. In this video, we have gone over a very simple example of context switching. Now, this example shows the core concept of it and highlights some of the trade-offs associated with swapping particularly processes in and out of the running state, but there is a lot further detail that you will see in the lectures. And we've also introduced the idea of having execution states for processes and threads, and we've introduced the two-state model. However, you will see more in-depth models in the lectures. One thing for you to think about before you go into the lecture is how the trade-offs may differ, whether we are switching process contexts or thread contexts, and what would have to be done differently between the two. Now, this you'll talk about in the lectures, but maybe think about how what we've discussed in this video would be different when we are considering processes, which have all of the resource ownership associated with them, and threads.